All right, in this lecture, we're going to be covering frames of reference and displacement versus distance. This one is a little bit more involved than our first kinematics, but it's really going to kind of help you get an idea of how we look at the numerical and directional aspect of motion. All right, so the first thing that we have to consider is that any measurement of position, distance, or speed needs to be made with a frame of reference. All right, and frame of reference is really just kind of specifying where are you seeing this motion? With what perspective are you witnessing the motion? Let's take, for an example, a situation that you might actually experience. Let's take, for example, a bus. This is my image of a school bus. I'm going to zoom out so you can take a whole look at it. Some really hard-hitting artwork happened here, ladies and gentlemen. This is a really great image of a bus. And let's say that you are hanging out and you've decided to sit in the back of the bus. So there you are, sitting in the back of the bus. So considering you sitting in the back of the bus, I suppose it does or does not matter if you know how fast this bus is traveling. But let's say that this bus is traveling at 80 meters per second. If you look out the windows, you can tell that you're traveling 80 meters per second. But it doesn't really matter because to you, riding on this bus, hanging out, you are sitting still and you're aware that you're sitting still. So from your frame of reference, you're motionless. You have a speed of, instead of 80 meters per second, you have a speed of 0 meters per second. So that actually kind of simplifies your motion a little bit. From your frame of reference, you're not moving. You're riding on a bus. You have a speed of 0 meters per second. But say, for example, you are riding on the bus with a random hedgehog. Here he is. Here's your random hedgehog. Right? You and this random hedgehog are both hanging out. And both of you, even though the bus is traveling 80 meters per second, from your perspective, you're both motionless. Right? And from your frame of reference, if you and the random hedgehog are hanging out and this hedgehog starts moving, right, the hedgehog has its own speed, and its own speed, we'll say, is 5 meters per second compared to you. Right? So to you on this bus, the hedgehog is moving 5 meters per second down the aisle. That would be one frame of reference. That frame of reference would be on a bus. But let's take that same situation, that bus, and let's change your frame of reference. Here, your frame of reference is, instead of being on the bus, it's standing along the road. Right? So here, from your perspective, you're just standing there. You have a speed of 0 meters per second. And then you've got yourself a school bus. Right? This school bus, if it's driving past you, right, that school bus has its own speed, and that school bus has a speed of 80 meters per second. All right? And that 80 meters perspective is compared to you standing on the side of the road where the school bus is riding by. And in this situation, we've actually changed things up a little bit, because now if we put our random hedgehog back on the bus, right, if that random hedgehog decides to move down the bus at 5 meters per second, right, he's moving down the bus at 5 meters per second. Now, compared to you, you don't see a hedgehog walking at 5 meters per second. You see a hedgehog on a bus going 80 meters per second, and that hedgehog is walking on the bus in the positive direction, 5 meters per second. So what you see in your frame of reference is you see that hedgehog is moving 85 meters per second compared to you. Or let's say that our random hedgehog, instead of moving to the front of the bus, decides to move to the back of the bus. In that case, the hedgehog was moving backwards on a bus going 80 meters per second, and it was going backwards 5 meters per second. Now compared to you, the backwards hedgehog, instead of having an 85 meters per second speed, has a 75 meter per second speed, because the bus is traveling forward at 80 meters per second, and the hedgehog is moving backward at 5 meters per second. In either of these situations, right, 75 and 85 meters per second of the hedgehog moving on the bus while you're standing outside is a different frame of reference than you hanging out on the back of the bus with the hedgehog moving down the aisle. Here, the hedgehog is just moving 5 meters per second compared to you. That's it. Or if the hedgehog decides to walk back down the aisle, he's still moving 5 meters per second, this time toward you in the opposite direction. But there's no addition, because to you, the 80 meters per second of the bus doesn't exist. You're riding on it. You're experiencing the 80 meters per second with the hedgehog. So this is a very good example of a frame of reference situation. And in this situation, right, we've got you on the bus versus off the bus. For the most part, in your everyday life, right, we have one consistent frame of reference. Usually when we talk about frame of reference, we say that our frame of reference is Earth. And it's really easy for us to interpret our frame of reference as being on Earth, because we all happen to be on Earth, and without really having to specify, I ran at 3 meters per second with respect to Earth, you can tell somebody I ran 3 meters per second, and they have this understanding that your motion was with respect to the Earth. You were moving 3 meters per second on the Earth. And so in situations like that where it's unquestionable, it's just with respect to Earth, you don't always have to specify your frame of reference. However, anytime you've got a situation where there could be some confusion about your frame of reference, then it would be really helpful, and you're going to need to specify what your frame of reference is. So anytime there's a possibility for confusion, right? If you're traveling in one direction and the hedgehog is traveling in the other, and you have to determine, is your frame of reference going to be from yourself or from the Earth, you need to specify what that frame of reference was. So motion needs a frame of reference. Motion also needs to be given both a speed and a direction. All right, so we have in our example, where's my little hedgehog identifier? All right, so we said that our hedgehog had a speed of 5 meters per second. All right, that's great that your hedgehog has a speed of 5 meters per second, but in order for us to fully describe the hedgehog's motion, we need a direction, like north, south, east, west, up, or down. All right, the hedgehog could move 5 meters per second down. The hedgehog could move 5 meters per second west. The hedgehog could move 5 meters per second to the right. All right, we have to specify both the magnitude, or the total amount of speed that he had, and which direction that he was going. All right, for everyday motion situations, directions like north, south, east, and west are going to be perfectly fine. However, in physics, most of the time, it's going to be really helpful for us to have a coordinate axis. Right? And a coordinate axis is just an x and y plot system. Right? And if we have our x and y plot system, we can go ahead and we can describe any type of motion. And we can do it just by using positives and negatives. Right? If we're talking about the x-axis, along the x-axis, typically in physics, going to the right is positive and going to the left is negative. If we're talking about the y-axis, going up is typically positive and going down is typically negative. Right? So that gives us our boxes. Everything is positive here. The x is positive, the y is negative here. The y is positive, the x is negative here. And both the x and the y are negative here. And so this gives us a coordinate axis system, a system that we can use to consider and analyze motion. And there's a really neat thing about our coordinate axis, and that's that our coordinate axis can kind of be used any way that we want to use it. All right, so take, for example, this is our coordinate axis system. Right? And since we're in control here, right, we can determine which way our axis points. In a lot of everyday situations, it's going to make perfect sense for us to just align it so that the x-axis is horizontal to the ground and the y-axis is straight up and down. Right? As long as the x and the y-axis are 90 degrees from each other, you can organize it in any way that we want. So that means that if we're considering other examples, like if we have to consider motion going up a hill, we don't have to keep our x and y-axis straight up and down. We can actually instead, we can tilt our x and y-axis so that our x direction is headed straight up the hill, or our x is headed straight down the hill. Right? So that's going to work in our advantage because then we're not having to figure out how far above the x-axis we are. Likewise, it's really helpful if we're going to be considering something like ramps. Right? If we're considering ramps, it's going to be really nice for us that we could just say that, oh, the direction of motion was directly along this straight line. So I can turn my axis so that the direction of motion was right along the x-axis. And this is going to prevent us from having to complicate a situation and figure out, well, how far above the x-axis was our motion? No, we're in control. That's our x-axis right there. And that's going to be a really, really nice tool for you to use. And you can give any position by the x or the y coordinate, which means that you could also consider objects that are falling or moving up and down on a rope. Right? In this situation, right, we could say, oh, well, here's our x-axis, just like this, going up and down the rope. Right? So if you've got a little dude, here you are, climbing a rope, we can give him the x-axis for the rope. Or if a little dude is falling, you can tilt so that your x-axis is going to account for the falling of the little dude. But I'm going to give you a hint. In conventional physics, anytime we have objects that are falling or moving in the vertical direction, up and down, we tend to give that the y-axis. So that means an object climbing up a rope, like you climbing up a rope, we most of the time are going to say that's in the y direction. If you're falling, you're plummeting to your death right here, at least you're doing it with a smile on your face. We would typically say that your motion is in the y direction just because you're moving vertically compared to or with respect to the Earth. And that's actually going to come in handy when we do talk about falling objects and when we talk about the force of gravity. So consider those in those situations. Instead of talking about the x direction, we do in fact talk about the y direction. So we're going to keep U on hand, stick figure U, and probably also, alright, so we've got our less stick figure version of U. You broke your arm. That's really sad. And your stick figure version of U, both objects not to scale necessarily. But we're going to keep those handy with respect to Earth. So we can consider how we can use this coordinate axis to determine distance versus displacement. Alright, so we're going to consider distance versus displacement. In distance, alright, distance is easy. Distance is just the overall grounds that were traveled regardless of their direction. So take, for instance, our coordinate axis system. Alright, we're going to give it some units. Alright, so we're going to say that that's the 0 mark. And if you traveled, let's say you traveled 70 meters in this direction. Right? And then you decided to turn around and you traveled 30 meters in this direction. Alright, so you've traveled a total distance. What is the total distance that you traveled? Well, it doesn't matter the direction, so if we're going to consider the total distance that was traveled, it would be the 70 meters that you traveled one way and the 30 meters that you traveled the other way. So that means that your total distance would be the 70 meters plus the 30 meters to give you a total of 100 meters traveled. That's your distance. It's regardless of direction. And this makes sense because if you've ever had to run a mile, that's funny, I know you all do, you know that even though you didn't really go very far from start to stop, you know you traveled the entire mile. So we're going to use this version of yourself. I don't know why you didn't dress down for PE, shame on you. But you start here, right, and then you run back and around, and you go out this way, and you come back down, and then let's say you stop here. Right? The total distance that you covered, all of these little footsteps along the way, right? All of that was 1 mile. Right? That's your distance. It doesn't matter if you start and stop in the same place. Distance is just how far you went. That's why you are able to, while standing on a completely stationary machine with belts called a treadmill, I call them the dreadmill, all of those L's do count, and you can, while holding on to the bar, standing in a building, you can travel as many miles as you want by just moving along that belt. And you start and you stop in the exact same place. You didn't go anywhere, however, you traveled a distance of however many steps you took, right? You could have gone a mile, whether it was around the track on campus or on a treadmill. The distance traveled, the grounds that were traveled, was a total of a mile. Alright, that's distance, and that's the beauty of it. You could run in circles all day and rack up a ton of distance. But displacement's a little bit different. You see, displacement is just the change in position from initial to final of an object. Alright, so going back to our school example, right? If you start here and you stop here, displacement is going to be the change in position. Alright, so displacement, we have to consider direction. We have to consider your axis. So I'm going to make our start the origin. And in this situation, right, you started here and you stopped here, and all we're measuring in order to, let's focus that up, right, and all we're measuring in order to determine displacement is this amount here, how far from the starting point you actually are. And that's not a mile, that's in fact, that's a negative distance. You've actually traveled negative x, not a mile, because you're only this far away from the origin. So we can consider, for an actual numerical example, right, we could call displacement how far the object travels from the starting point. And we'll consider the example that I gave you before of let's say where did my Expo pen go? I'll use this one. All right, let's say you started here at 0. You travel 70 meters out this way, and then you travel 30 meters out this way. All right, it means that even though you went a total distance of 100 meters, your displacement is just how far from the origin that you are. This is your displacement. All right, and so if we consider this, right, you went 70 meters this way and 30 meters this way. So it turns out that your displacement between here and here is actually only 40 meters. That's your displacement, and it's in the positive direction in this situation. So that means that your displacement in the example where you traveled a total distance of 100 meters, you were only displaced 40 meters. And that's the difference between distance and displacement. Right? To consider the actual values, one of the things that we can say that helps us out is that displacement has a size, which we call a magnitude, and a direction, right? Distance was regardless of direction, but displacement has an overall size, right? 70 meters this way and 30 meters this way, so it has a size of 40 meters displaced, and it also has a value in the positive direction. We could also consider a situation where the direction was negative instead of positive. Say, for example, you traveled 70 meters this way and 100 meters this way. Right? If we say that we imagine we started at the origin, right, then in this situation we'd end up actually being negative 30 meters. Right? So let's take a look at that. Right, if we started by going 70 meters this way, right, and then we turned around and we went 100 meters this way, our displacement is now here, negative 30 meters from the origin. All right, so we can have a magnitude, which is the total amount, and a direction. And when we're using a coordinate axis, the direction is positive or negative. And we can flip those signs and manipulate them however we want. But in general, it's nice to have the convention of the coordinate axis system and positives and negatives. So that means that when we talk about displacement, we're actually talking about a vector. All right, vectors have magnitude and direction. In a diagram, they would be represented by an arrow. So here's a diagram. The spherical cow. All right, and the spherical cow could be traveling in that direction with a value of 5 meters per second. And that would be the diagram. We've reduced it down to its translational motion, just the dot. And it's going in that direction at 5 meters per second. So this is a great representation of a vector value. Like displacement, that has a size, right? Here's 5 meters per second. and a direction. That's the direction that the arrow is pointing, and that's exactly how we represent them. So displacement is a vector, and it's really important that you remember that displacement is a vector because it has a size and a direction, not because somebody drew an arrow on a piece of paper. Here you've got a delta value. Any value that has a delta next to it means change in. Right? So delta x means change in position along the x-axis. If we wanted our position along the y-axis, then we would say delta y instead. Right? And delta x change in position just means the final position minus the initial position. How much the difference between these two positions is. All right, so let's take a look at an example of the final position minus the initial position. All right, and in the first example that we're going to take a look at, we could say that our first position is at 10 meters. So x1 was at 10 meters, and we'll say that x2 was at 30 meters. In the book, one of the things to pay careful attention to that I didn't do just now is that the book actually says 10.0 meters and x2 is 30.0 meters. So these are very precise measurements. All right, so we can actually take a look at what happens in this situation. We can give our axis values, right? So we'll say that that's 10, 20, 30, 40, and that's meters on the x-axis. Right? And this is just going to help us visualize it. Right? Our initial position was here, and our final position is here. Alright, so that means our displacement is here. Alright, our displacement is the difference between this 10 and this 30. Alright, and we need to know, did we travel in the positive direction or in the negative direction? Well, we displaced to the right. So that means that if we're going to calculate our displacement, right, we're going to need to consider the final minus the initial, and that will give us the difference between the two. So that's 30 meters minus 10 meters to give us a total displacement of 20 meters, and that was in the positive direction. You could actually write the positive or just infer the positive by not writing negative. All right, and that would be a displacement in the positive direction. And it's a displacement because it has a direction and a size. Conversely, we could consider a different situation. All right, and in a different situation, we could have started at 30 meters and ended at 10 meters. All right, so let's take a look at that situation. In that situation, right, I can use the same axis, but this time we started here, this is our x1, and we ended here, this is our x2. Our displacement is going to be the same magnitude, right? Because there's still the same size of difference between them, but this time we traveled to the left. And so let's determine what that value is. In this example, right, x2 minus x1 is going to be 10 meters minus 30 meters. So our delta x is going to be a negative 20 meters. All right, so same magnitude, but the direction is different. Our vector is different for this. So that gives us a really good idea of how this coordinate system for distance versus displacement really works. We're going to be working with that in class a little bit, so be prepared for that. All right, that's going to end that one.